Alright, so welcome back. Today we'll be doing a full comprehensive tutorial on how to load a part into Mastercam, program it, and create the toolpath necessary to cut out certain geometries. This is the part we'll be working on. It's an output shaft for a gearbox. As you can see, there's a few operations we're going to have to do here. One being the hex pattern on the top here, as well as the internal grooves found on the inside of the part. So I have the part open in Solidworks right now, and what I'm going to do is I'm simply going to save this part as a step file. So a step 214, select that, and we'll save it to our parts folder. Alright, and now we will open Mastercam, and we will open this part in Mastercam, and we will begin the programming process. Alrighty, so we have Mastercam open now, so let's import the part and begin programming. I'm using the educational version of Mastercam, so yours may look a little different, but they're almost all the same. So let's open this part. So you're going to go to the File selection, and you're going to go to the Merge tab. And it's a little strange compared to normal SolidWorks, as in you use the Merge tab to open the file. You go to All Files down here, and we will go to the folder we saved the part in, and we will open the step file for that shaft. Okay, so we've opened the part in Mastercam. Now it's important to just say yes to this, and we're going to save this in Mastercam as a, call it output shaft. Mill. Alrighty. So now we need to import the machine definition for the machine we'll be running these parts on. I'll be doing these operations, the internal grooving and the outside hex, on a milling machine. So I'm going to go to the Machine tab, and I'm going to go to Mill, and I'm going to open the post processor that we use for this program. Alright, so we've loaded our part into Mastercam. We've gone to the Machine tab, we've selected Mill, and we've selected our desired machine definition. Now we will create a plane, and this plane is also commonly known as the work coordinate system, and it's where the machine 0 will be set in order to reference the tools from and reference all the other toolpaths from. So it's very important. Tips for setting the work coordinate system. You want to set the work coordinate system in a spot that's actually reachable and measurable on the CNC machine itself. Because if you can't get to the actual point in which you set your system or your origin point, you won't be able to set it on the machine and it will not work. So for round parts such as these, I like to set my work coordinate system at the center of the part, or in a round bore such as the one found up here. And I like to put the Z, so the height of the part, at either a flat plane and with a specific length offset from that plane, or at the top of the part. So let's go to the Planes tab and create a new plane. We'll go from solid face. We'll select the bottom face, and we'll call this plane Op 1. Alright, so we've defined Op 1, and you can see it's defined down here at the bottom. So what we want to do is we want to set this as the work coordinate plane, or the current plane. So we'll set this equals button, we'll highlight that, and we'll click this, and that'll set it as the work coordinate system, the coordinate system, and the offset. So if we take a look at our Op 1 plane, we can see that the Z direction is going is going this way. It's going up, and that's not ideal for our programming, because we want the tools. The tools are going to be coming in from this side, so we want the Z direction to be the other way. So we're going to rotate the Z as well as move this point up to approximately here on the part. And the reason we're doing that is for when we cut our soft jaws, we'll set the top of the jaws as this point, and we will reference our bottom of our jaws to the bottom of the part. So let's do this. We'll edit this point. We'll rotate this 180 degrees. You can either type in the desired number or just rotate it by hand until you get to the correct angle. Type in 180. Say yes. And then by highlighting the line of the Z-coordinate system itself, clicking, we can actually slide it, and it'll snap to specific geometries on the part. So we'll just select this bottom ring. There. And we can see now this origin is in line with this plane, or this flat of the part. Alright, so congratulations, you've set your work coordinate system, so it's time to create some toolpaths. So making sure our current Op1 is selected, we're going to go back to the toolpath slide, and we're going to create a toolpath. So by right-clicking the white box over here, you'll have the option to do Mill Toolpaths, and then you can see we have all of these various toolpaths here. We have contours, 2D high speeds, drill operations, 3D surfacing, 3D high speed toolpaths, which is like a 3D roughing, area roughing, scallop, and there's many options. We're going to be very basic in this, and we're just going to do a simple contour. Alright, so we selected contour, and the first thing we're going to tackle on this part is cutting this hex out. So we have a few different ways that we can select what's referred to by Mastercam as the chain of the part. The chain is the geometry that the code will follow when it's cutting out, that the tool will follow, when it's cutting out the part. So by changing these different selection methods, we can either do a loop, so that's what the option we're in right now, so it'll select an entire continuous loop, or we can do a face selection, in which it'll just allow you to select faces of a part. You can do an edge, which would just be a single edge, or you can do a partial loop, in which it'll only do part of a continuous loop. There are also other options, and you can use them as well, but I find myself using the edges, loop, partial loop, and face the most often. If you look up here in the mode tab as well, there's also an option to do wireframe selection. A wireframe is a sketch or a drawing that's created on the part in Mastercam that's not a solid model. So if you go to the wireframe tab of Mastercam, you can create circles, arcs, squares, rectangles, whatever you desire on the part itself, and you can select those as geometries for toolpaths as well as just the solid part. This wireframe becomes extremely handy if you need to do a specific operation on the part that was not modeled by the original designer. You can simply change it here and do the toolpath as you need it to be made for the manufacturing of the part. So let's go back to the Solids tab and select the loop command, and we'll select this top loop of our rectangle. Oops, I accidentally exited out. So we'll go back into the geometry, add, I'll bring this back to this tab, so we'll go loop, select the top loop, say yes. And it's important to note here that our yellow arrow defines two things. it defines the direction the tool will go around the part, as well as the side of the contour that the tool will remain on. So this arrow indicates that the tool will be on this side of the part, and this arrow indicates that the tool will travel clockwise around the part. This arrow will change, this larger arrow will change depending on if you are climb milling or conventional milling. Most likely, for any parts you're going to be making, you're going to want to be climb milling. Conventional milling is very rare on a CNC machining center, and it only has very specific applications. This is not one of those. If this arrow was flipped to the other side, or this larger arrow was going the wrong direction, you can simply go into the Geometry tab, select the solid chain, right-click, Edit, and it will bring you back into this option, in which you can change the start point, so where the contour starts along the entire loop, the direction in which it goes, as well as the selection method. So if you meant to only select one line instead of an entire loop, you can go in and deselect the loop and reselect the one line. I'm pretty happy though with how Mastercam has automatically defined this loop, so I'm going to leave it as B. Alright, so we've selected our geometry. Now it's important to create our tool and tell the machine how fast the tool needs to move in order to cut the part out. So let's go into the parameters, and this brings us to the parameters of the toolpath. There are a lot of options here, so we'll just talk about the very bird's eye view of them and what's the most important. So in the Tool tab, this is where we will define our tool, the size of our tool, and the speed at which the tool will move, as well as the speed of the spindle when that tool is being used. So by right-clicking this box, we can create a new tool, and we have all these different options of tools that we can use. Flat end mills, bull end mills, ball end mills, face mills, radius mills, chamfer mills, the list goes on. You can also see that there's options for drills, counterbores, reamers, spot drills, counterthinks, and even very specialized tools like taper drills, oval drills, and barrel drills. For us though, we're just going to be using a simple 1/2 inch flat end mill. So let's select the flat end mill, hit next. Now I know, according to the manufacturer's specifications, my tool is a 1/2 inch in diameter. Its overall length is 2 inches. Its cutting length is 1 inch. And its shoulder length and shoulder diameter are all correct. I also know that the tool has 5 flutes, and we'll call this tool 1/2 inch flat end mill roughing. You can see there's a lot of other options here. Tool number, length offset, diameter offset. You can even change the manufacturer of the tool, as well as many other options. For us in our applications, we're going to leave these as B, and we'll change them a little later. Alright, so this tab is where we will change the feed rate, spindle speed, as well as the surface footage per minute of the current tool. If you know the tool number that the tool that you'll be using for this application will be in the machine, you can also change that here. My tool is in, my 1/2 inch end mill is in tool slot 16, so I will change that tool number. And you can see that we'll also change the length offset as well as the diameter offset for that tool. So now let's change the feed rate and the spindle speed. I know that my tool needs to be run at 40 inches per minute for high speed for heat treated steel, excuse me. And I also know that my surface footage per minute is going to be approximately 350. You can see by changing the 350 of the surface footage per minute, it will change my spindle speed and my feed rate automatically. Now, although the feed rate is much faster than what I originally programmed, I know that this tool runs best in heat-treated material at 40 inches per minute. Although my spindle speed and my surface footage per minute can remain as 2674 and 350. Let's take a look at the cut parameters tab. This tab is where we define our cut and how it's going to operate and other little parameters about the tool itself. The compensation type is the side of which the tool is cutting on, and as well as the tip compensation defines if the tool is going to be defined from the center of the tool or from the tip of the tool. These can all be remained or left as normal. The contour type is the defining if the tool will be following a 2D path or 3D path, or if it's going to be doing a chamfer operation. Our tool is a 2D profile. There's no 3D movements there, so we're going to leave that as 2D. Our stock to leave is fairly important. This is a good application to use if you're machining a precise fit, and I know that this hex here needs to be a very precise fit with a separate part, so I'm going to leave 10 thou material on the walls of this hex and then create a second operation that I can use to remove that 10 thou very accurately. I will also leave negative material on the floor, and what this will do is it will place the tool slightly below the bottom of this part to not leave a lip or a very small thin burr at the bottom of our hex pattern. Let's go back into the parameters tab and move to the next option. Depth cuts, we'll be doing this at one full depth with multiple step overs, so we can skip this tab. Our lead in and lead out, this is an external or a outside profile, so our lead in and lead out can remain at 0.5. Breakthrough, we don't need to worry about this currently. You can either change the negative stock to leave here or the breakthrough. They both have the same effect. Now, multiple passes. This material that we'll be cutting here is heat-treated material, so it's fairly dense, fairly hard. So we're going to have to create multiple passes around it to fully remove the material. So let's check the multi-pass option. We'll do 9 passes, and we'll do a 0.008 step over for each pass. We'll select this option here, keep tool down, which will prevent the tool from raising and lowering for each pass. Let's next go to the linking parameters tab and select the depth. So this is a very important tab. This tab defines the top of the part, bottom of the part, top of the stock, and the point at which the tool is safe to move across the part. This is a fairly simple part, so we'll be doing a very simple layout here. We'll just select clearance, and we'll set it as a nice 2 inches, which means it'll be 2 inches above our bottom of our cut. The top of the stock we will define as the bottom of our cut, and the depth we'll switch its selection to absolute, and we'll also define it at the bottom of the cut. Our feed plane can remain at 0.2 and our retract can remain at 0.25 as well. So now you should have selected all the possible operations to create a viable toolpath. Other things that are important to check is your planes tab. You want to make sure that the work coordinate system, tool plane, and the comp and construction plane are all op1. If this is not the case, it may be necessary to go back in to the planes tab and reselect the correct work coordinate system or plane for that current toolpath. All right, so let's say OK, and let's see what we have. All right, so we've created a viable toolpath. As you can see, the tool will start at this green entry point. It'll go around and it will cut this hex pattern 9 times, stepping in 1/8 thou on each pass. Now that may seem very small, and in this case it is very small, but that's just because of the material we're using. If this was aluminum or brass or a much softer material, we could be much more aggressive in our machining strategy. So let's take a look now at creating a finishing pass for this part. So we'll right click and we'll say copy, and we'll paste this, creating a second operation of the same type. We'll go into the parameters tab, we'll go into multi-passes, and we'll decrease the roughing passes to 0, and we'll set our finish pass to two steps. Since we left 10 thou originally on the walls of this part, we will take a 5 thou step over with 1 spring pass. A spring pass is a pass taken at the end of a cut that removes no material but is simply just following the geometry. It helps to prevent or compensate for tool deflection or any chattering that may have occurred in earlier operations. Since we copied and pasted our tool path, we know that our linking parameters, cut parameters, and tool type are all selected. I'll be using the same tool for roughing and finishing this part as I did for, let me rephrase that. I'll be using the same tool for finishing as I did for roughing for this part, so I'm going to leave this as B. The only thing I'm going to change is the feed rate. I'm going to decrease it to 25 inches per minute, and that will just go a little slower, which will create a better finish around the hex. So, congratulations, you've successfully created your first toolpath in Mastercam. Next, I'll be going over some of the simpler skills or some of the easier things you can do within Mastercam to ensure that your toolpaths are doing the correct things. So, how do you know that your toolpaths that you've created are cutting the correct geometries? Other than knowing that you selected the correct geometries, it can be difficult sometimes to know exactly what the toolpath is doing before you run it in an actual part and get to see real results. So one thing I like to do is create what's called a stock model. A stock model is used to simulate the operations and provide a visual display of what the part will look like after it is done being machined. So let's go to the Toolpaths tab and select stock model. A stock model, by selecting that tab, it'll bring us up to this tab right here, or this window. We have a few different options here. We have to set a few parameters, and then we can select our toolpaths to simulate and get a look at what this part's going to look like. The first thing to do is to select the type of initial stock shape. So what kind of raw material are we going to start off with to make this part? This part is made out of cylindrical material, but we can see that it's trying to center the cylinder of the material along the x-axis. But we know that when we set this op1 tab, we set our z-axis to be the long ways of the part. So we're going to go to the axis tab and we're going to click Z, which is going to place that stock on the center axis of our z-plane, or z-axis, sorry. Now, if your stock had an initial diameter and initial height, you could load those in right here and simulate that. I'm simply going to leave this as B and create my stock this way. So one operation I like to do for actually creating the stock itself is what's referred to as the bounding box. If we select bounding box, click and drag over our part, we can select all solids. We can end this selection, and Mastercam will create a initial stock shape around our part. Now, this shaft was originally created on a mill, so it's a the post-ops that we're doing to this, as far as the hex pattern and the internal grooves, are mostly done already, which is fortunate for us. So we'll be taking a look at, though, how the part would have been cut from original stock. All right, now going to the Source Operations tab on the side and selecting both of our toolpaths, we can then click OK. And we can simulate what the end product is going to look like on the machine. As we can see, our two toolpaths are going to do an excellent job at cutting out this hex pattern. You can also see that the stock has a little bit of material still left on the edges, which is most likely due to our stock to leave that we defined in our second contour. So if we decrease this stock to leave on the wall to 0, and then we select our stock model and use the regen button, now you can see that the stock, or the gray, is pretty much gone all the way around the part, which means the tool is cutting completely up to the edge of the hex. Another operation, or another thing you can do, is go to the Levels tab, and you can turn off the visibility of your part and have a look at the stock simply on its own, which provides a much better view of if there's any unnecessary or unwanted gashes or gaps caused by perhaps a toolpath that you forgot to change the height on, or the retract distance of a tool that may have moved across the part at the wrong height. So let's turn the part back on. Back to our Toolpaths tab and take a look at what we've done. So this is these toolpaths will work just great to remove the material we need. One thing that's important to mention is that this, however, does not show you how the toolpaths will work throughout the entire cut. This is only the end result. So although it may seem like these toolpaths will work, which they will, if you had not done enough step overs in your original operation, defined right here, the tool that when the tool is run initially in the part, it could create too much work on the tool and possibly break the tool. So this is only to be referenced for the final shape and the kind of verification of your toolpaths. However, it is not viable to use to check the operation itself and how the machine and the tool is going to run through the entire cut.